All right, here's our topic. Here's our objective. And what it means is if I know some concentration, if I know the graphs of different the concentration, how it changes over time, I should be able to look at a graph and determine the order of the rate law with respect to that given reactant. And I should also be able to calculate the rate constant value for that given reaction. Now there's only one graph here shown, but there are going to be three graphs, one for zero, first, and second order that we just need to commit to memory. This happens to be the graph for first, it's not for zero order. It's showing you that regardless of time, regardless of concentration, that the rate remains constant. All right. I just want to review a couple things. K is your rate constant value. It's a proportionality constant. It's just a number. And the order is the exponent of the given reactants. All right. And how that the order expresses like how when the concentration changes, how that will affect the rate. All right. And this is all we're going to use the Beer-Lambert law, where if I do serial dilutions or I do, look at different concentrations, I'm going to see a linear pattern there where the absorption is going to go down or up depending if you're making it more or less concentrated. All right. And we're going to vary the concentration. Now, here are the steps. This is a lot of information on how to do it. I wrote it out. I'm also going to talk about it with visuals on how we'd calculate it. So first of all, we need a reaction. And this reaction is good for spectroscopy because you'll notice it goes from purple to colorless. So as the reaction progresses, the solution is going to become less and less concentrated by color. Therefore, if I run this thing, if I use that thing with a spectrometer, all right, that'll help me chart how the reaction is progressing, how fast it's going. The first thing I'd want to do though is I'd want to perform a standard curve, a calibration curve. Now it says here, or it shows this is purple. Sorry, this is green. You see it's purple. It's actually not green. It was, if you were to do it, it would be purple, but I didn't get an image from that had purple. And then I'm going to do these serial dilutions and I'm going to chart my absorbance. And from that, I'm going to get a graph. I'm going to get a calibration curve. And I'm going to need this line, this regression line, to help me calculate the molarities. And then I'm going to run the reaction. All right. So this is what the chemicals actually look like. It's pretty incredible how complicated that is. But this is just like a shortened version of it, simpler. And I'm going to run it in the chamber, in the spectrometer, and then chart the absorbance as time goes on. And then I'm going to take that absorbances, take all those absorbances, plug them into my regression line, and calculate the molarities as the reaction is progressing. And that way I can make that molarity and turn it into three different graphs or three different numerical values. One being, I'm actually going to turn it into two because one is just the concentration, and it's X because in general this is going to apply to any reaction, the natural log of X and the inverse of X, and then I'm going to chart them all, and we're looking for a linear relationship. All right. Now, one, I made a line graph, and two of these I made scatter plots. You can see which one is linear. This one is linear. Now, what that means about the reaction is that it's first order with respect to however I've set my parameters. So, as I had mentioned before, this is the zero order graph, and this is the first order graph now. And the k value, or the rate constant, is this going to be the negative slope value. So you can see these are negative slopes. I wouldn't have a negative k value, else the rate wouldn't exist. Rates have to be positive, unless you're talking about like a disappearance. But even then, it tends to be a positive you don't tend to talk about it like a negative value. Um, the k value is just the negative. It's this whatever the slope this is, and I make it a positive number. Now, if it's second order, the linear graph is the inverse. All right, and my slope is just the value of the k value is just the slope, because that's what I wanted to say. All right. So just to apply this to the to the graph we studied, or that reaction we studied, here is our graph, and there's our regression line. Here's our slope. All right. So our k is the negative. So I take that and I just make it a positive value, and then I would add units. And since it's first order, my units are going to be this should just be m. It shouldn't be inverse seconds. There's a mistake there. It should just be inverse seconds. And here are my sources. Uh, just remember that k value is off. That unit's wrong. All right. Here are my sources. Thank you so much, and hope this helps. And have a good day.